Hey guys, Miss Peterson here, and welcome to AP Physics 2, Lecture 4-3, all about capacitance. So this is the lecture where we're going to put our electrostatics knowledge together with our circuits knowledge and the properties of capacitors. We'll also look a little bit about capacitors in series and parallel and capacitor-only circuits. So before we get into it, let's talk about what a capacitor actually is. Okay, a capacitor is two charged plates, and we can charge it by connecting it to a battery. So, okay, if we can kind of visualize this, we have that two charged plates. So if I apply a potential difference to them, okay, that is going to push the positive charge onto this plate, which will repel the electrons in this plate. Which will attract the electrons in this plate and allow that positive charge or that current to keep flowing through the capacitor until it looks like this and is what we consider fully charged. We can see here that the voltage across the capacitor matches the voltage of the battery. Okay. Now, the energy of a capacitor is stored in this electric field. So if you're thinking about, okay, well, how can we increase the capacitance? How can we make it store more energy? A couple different ways we can do that. We can make a bigger electric field. One way to do that is by separating the plates. Okay, so they're oppositely charged. They want to attract. So to pull them farther apart, we have to do work. We have to separate them. We have a bigger electric field, which increases that stored energy. Okay, so that's one way we can go about it. We can also change the plate area. So bigger plates are able to store more charge. Okay, if I connected it back to the battery, we can see how it would get that higher voltage and more charge there. When it's disconnected from the battery, note the actual charge itself has no place to go. I can play with the values of it, but that charge doesn't have anywhere to go. But it can go somewhere, okay? We could use the capacitor to light up that light bulb, okay? And using that energy, it acts kind of like a battery, but with a limited supply, and will discharge as current flows, and it lights the light bulb until there's no more charge imbalance left on that capacitor, okay? So that's what a capacitor is. The equation for capacitance related to its properties is that the capacitance equals kappa epsilon naught A over D, okay, where K is, of course, the capacitance. Now, capacitance is in units of farads, okay? So farads, which we'll get to in a sec. K, kappa, is called the dielectric constant. Okay, that's K. And what it is it's a measure of how good the insulator between the plates is. For air, it is 1.0, and it is just a ratio, so just 1.0. Anytime you add a dielectric, okay, you're always going to increase the capacitance. Okay, adding dielectric will always increase the capacitance of a capacitor. Okay, they're often made of insulators, which means that their actual molecules can be polarized. So if you kind of picture a situation here where we added a polarizing material, spread this out so you can see it, where we added a polarizing material between the plates, that could be polarized and increase the value of that electric field strength, thus increasing the capacitance. And then epsilon naught is the permittivity of free space. Now, this is one of the constants on your AP Physics 2 reference sheet. It's called Coulomb's law, or epsilon naught permittivity of free space, and it has a value of 8.85 times 10 to the negative 12 Coulomb squared per Newton meter squared. Okay, Again, units are just kind of made up to make this equation work with our definition of capacitance. Okay. Yeah. So that's epsilon naught, the permittivity of free space. A will be the area of a plate, of a single plate, in meters squared, and D is the distance between the plates. Also in meters. Okay. So that's what a capacitor is. Okay. Now in circuits, okay, the capacitance depends on the capacitor. But on your equation sheet, it's written as delta V equals Q over C. So if we rearrange that, we can see C equals Q times delta V. So basically, a capacitor and the capacitance is how good it is at storing charge, how much charge it will store when a certain potential difference is applied. Okay. When we use this equation, obviously the charge on one plate is going to be positive and the charge on the other plate is going to be negative. So if you took the total charge, it would just add up and cancel each other out and be 0. So when we use this equation, Q is going to be the charge on one plate in coulombs, okay? And yes, the units for charge is coulombs, which is a C, but the variable we use for charge is Q. And for capacitance, the units is a farad, which is an F, where 1 farad means 1 coulomb per volt. So for 1 volt applied, you would store 1 coulomb of charge. And its symbol is a C for capacitance, and its unit is F, not C. C is the units for charge, coulombs. Yeah, okay, remember that. So 1 farad is like a really high capacitance. Most capacitance that we'll work with will be in either microfarads, okay, microfarads, which is times 10 to the negative 6 farads, or even nanofarads, which is times 10 to the negative 9th farads. Okay. Now, for the energy stored on a capacitor, okay, it's stored in that electric field. Okay, so you might remember from our electrostatics unit that the potential energy of an electric field equals Q times delta V, that voltage that you have to apply. Now, if we apply this to a capacitor, okay, we have some voltage of the battery, and it is going to push that charge on to the capacitor, okay? And that's going to repel charge here and flow there. So you can think of the change in the energy of the capacitor as the work done to create that electric field, okay? So the energy of a capacitor equals Q, okay, the charge that you're moving, times delta V, where that voltage is your voltage of the battery. However, the voltage of a capacitor is not the voltage of the battery the whole time, okay? That charge builds, and it adds, and it adds, and it adds. The voltage starts at 0 and then goes to the voltage of the battery. So the average voltage, you can kind of think as 0 plus V battery over 2, or V over 2. So in our equation for the energy of a capacitor, we have a factor of 1/2 there. So 1/2 Q delta V. It's also in one other form on your equation sheet, where they're putting, instead of the delta V, they're subbing in the Q over C, which gives you 1/2 Q squared times that capacitance. Okay, so that is for the energy stored on a capacitor. 1/2 Q delta V, or 1/2 Q squared C. Okay. If you want a kind of more in-depth derivation of it, or a calculus-based one, hyperphysics has a great one where you really think about the energy of the capacitor is the amount of work done to move those charges across that voltage. So if you're thinking of that integral of from 0 to a full charge Q, of moving it across that voltage, you get that 1/2 Q squared over C. Okay, so the calculus way to derive it. Now, let's go ahead and apply it. Okay, we have a capacitor is made of 2 plates, 10 centimeters by 10 centimeters. Okay, so let's go ahead and write down everything they give us in the problem. Okay, we have a capacitor where the area of the capacitor is 10 centimeters, so 0.1 meter by 0.1 meter, or 0.01 meters squared. Okay. We have the distance between the capacitors is 0.1 millimeters, so 0.1 times 10 to the negative 3 meters, with a 100-volt battery across it. Okay, so we got 100 volts. Okay, the switch is closed and the capacitor is allowed to charge. Okay, first one says find the charge stored on the capacitor. Okay, well, first, in order to do that, I probably need to know the capacitance of the capacitor, because to find the charge stored, I know I can use delta V equals Q over C, but I would need to know C for that. I do have enough information to find C here, though. So we can use our equation for capacitance. Capacitance equals kappa epsilon naught A over D. Again, kappa, unless they say otherwise, just assume that it's air as your dielectric, which has a K of 1. So then we have epsilon naught, which is 8.85 times 10 to the negative 12 Coulomb per Newton meter squared. Okay, and then the area of the capacitor, 0.01 meter squared, divided by that distance, 0.1 times 10 to the negative 3 meters. Okay, close that off, and we get a capacitance of 8.85 times 10 to the negative 10 farads. Okay, now if you're interested in how those units work out, we got the meters squared canceling out with the meters squared. Okay, so that gives us a capacitance per Newton, which is a kilogram meter per second squared times another meter there on the bottom. So it is really coulombs per kilogram meter squared per second squared, aka joules. So joules. Yep. So C is for coulombs. I was thinking C for capacitance. I made that mistake. See, this is why it's dumb. Coulombs per joules. Okay. And we know that energy per charge per volt per energy is what a farad is. Okay. So to find that charge stored on it, we have Q equals C delta V. So we just plug in those numbers. Okay. 8.85 times 10 to the negative 10 times 100. Farads times 100 volts, and that gives us a charge stored of 8.85 times 10 to the negative 8 coulombs. And we can then find the energy stored using our energy equation. Energy stored on a capacitor is 1/2 QV. So I got 1/2 times 8.85 times 10 to the negative 8 coulombs times 100 volts. Okay, looks like a very similar calculation when the farads and the charge are the same, just off by 2 orders of magnitude. So the energy stored is going to be 4.43 times 10 to the negative 6 joules. Okay. Now, for the electric field strength, what equation are you going to use? Okay. There's two different ones that will work well. You can either use that the electric field is the change in voltage over that separation distance, or the electric field equals Q, the charge, over E naught times the area. Both of these will get you the same value for that electric field strength. Okay, so plugging in either 100 divided by the separation distance, or by plugging in Q, the charge. Okay, by Q, the charge, over epsilon naught, which is this constant, times the area. Both of those calculations will get you 1 times 10 to the negative 6 newtons per coulomb. Okay. Ooh, and now we're going to talk about increasing the plate distance. Okay, the switch is now opened. Okay, note whenever we have the switch is now opened, okay, that means nowhere for charge to go. So you don't have a complete circuit. You're not going to have any current, which means current is the flow of charge. So the charge on the plate will not change. But what about the capacitance? Well, okay, if the distance between the plates is increased, is that going to mean it's better at storing energy or worse? Okay, well, if the plates are spread apart, you have more distance between the plates. So you're going to have more capacitance. Or in equation form, okay, A over D. Okay, if D goes up, the capacitance will decrease. Okay, the capacitance will decrease. Okay, again, they're further apart. You got more field. So let's go ahead and discharge it real quick. And then we'll go ahead and start with our plates close together, so we can kind of visualize this. We have that high capacitance. Okay, we'll apply that voltage, put all that charge on there, and now disconnect the switch, open that circuit, and separate the plates. As I separate the plates, we see that the stored energy goes up, but the capacitance goes down. Okay, capacitance is how good it is at storing for the volt. So you'll have less charge for that voltage, but you'll have more voltage there. Okay. Exactly, the voltage across the plates. Okay, that comes from delta V equals Q over C. So if we have, okay, a lower capacitance, that will increase the voltage across the plates. Okay, voltage is that energy per charge to move it between those. If you have a bigger field, they're more spread apart, you're gonna have more voltage there. That will increase. Okay, same with the energy stored. Okay, voltage is the energy per charge. So if the energy per charge increases, the total energy will also increase. Okay. And you can always think of that one from U sub C equals 1/2 Q delta V. Q stays the same, but delta V goes up. Okay. And the electric field strength between the plates. Well, the electric field strength, remember, is that voltage divided by the distance. So if we have the same, the voltage increases and the distance increases, okay, they're actually going to increase proportionately. Okay, so the electric field strength between the plates will stay the same. Okay, increase, and this will actually exactly double. Both of these would exactly double if you double that distance. Okay, and the capacitance would half. Okay, cool. Okay, cool. Okay, last thing, let's talk about capacitors in series and parallel. Now, in terms of the math of it, the rules for adding it are the opposite for resistors. Okay, so if you think about the potential difference, let's go ahead and draw these circuits so you can kind of visualize it. Okay, first let's draw the series. So we have our battery, and then we'll have a capacitor here and a capacitor there. Okay, where in the parallel, we'll have the battery and a capacitor here and a capacitor here. Okay, so let's think first about the voltage. Okay, voltage is the same. Voltage doesn't change. So in a series circuit, it will be shared. Okay, so if this is C1, this is C2. Okay, C1, C2. Okay, it's shared. So the voltage of the battery will equal the voltage of C1 plus the voltage of C2. Where we know in parallel, it's always going to be the same. So the voltage of the battery will equal, and I should be specific, the change in voltage across the battery will equal the voltage drop across capacitor 1, which will equal the voltage drop across capacitor 2. Okay, so there we go. We got that. But now let's think about that charge. Okay, we got C equals Q over delta V. So if these have the same capacitor, but they're each going to have half of that voltage, okay, they're going to have the same charge on them. And it's not going to be the full charge of all of it, okay? Because you can kind of picture as this charge builds up here, okay, it is causing the charge to build up here, which is causing it to build up here. Okay, there's nothing in between that would change the relationship between those charges. So they end up being the same on all of the plates. Okay, so charge is going to be the same, where the total charge that is usable in the circuit will equal the charge on capacitor 1, which will equal the charge on capacitor 2. But in parallel, the battery, okay, you can kind of think of it as pushing on to each capacitor independently, okay? So each capacitor is seeing the full voltage of the battery. They're both stored in their own circuit. So the charge is going to be adds, okay? Or you can think of it as like shared, where the total charge in it will equal the charge on capacitor 1 plus the charge on capacitor 2, etc., etc. Okay? So, because each capacitor has that same charge and they're only getting half of that voltage of the battery, okay, the total capacitance here is really going to be less than the capacitance of each individual capacitor, because it's just not going to be as good. And it ends up being the equation is 1 over the capacitance of a series circuit equals the sum of 1 over each individual capacitor. Okay? Because again, they can't act and give their full charge to something, because they can only give their charge to the next one, which will give it to the next one, etc., etc. So that total capacitance ends up having that inverse relationship. Okay. And you could see it also here if we were to reorganize this equation and solve for the charge stored. Okay, we get Q, solve for the voltage. We get Q over C. So you can see that total capacitance would be on the bottom. So if we had the voltage of the battery, it would be Q total, which equals over C total equals Q of C1 over C1 plus Q of C2 over C2, all of those Q's are the same, so they can cancel them out, and you can see where that equation comes from. Where in parallel, they're each individually storing that. Okay, so all of that charge can be used. So the total capacitance of a circuit or the capacitors in parallel will just equal the sum of the individual capacitors. So you can see here the total capacitance would just equal the capacitance on 1 plus the capacitance on 2, since they each store their own charge and each have that full voltage of the battery. Okay, cool. Okay, cool. Let's go ahead and do some example problems and solve some capacitance circuits. Okay, let's start with 3 capacitors, a 3 microfarad, 6 microfarad, and 9 microfarad, are connected in parallel to a 300 volt battery. Draw and solve the circuit. So they are in parallel. So we have a 3 microfarad capacitor, a 6 microfarad capacitor, and a 9 microfarad capacitor. Yep. Zoop. And we have a 300 volt battery. So they're in parallel. What's going to be the easiest for us to solve first? Yeah, okay, we know those voltages. The voltages across each capacitor will be 300 volts. So it is delta V equals Q over C. So Q equals delta V times C. So the C, I'm going to actually put it in units of microcoulombs just to make our math a little bit easier. Okay, so we have 3 times 300 for a total of 900 microcoulombs. Okay, if you're doing it in regular, it'd be 9 times 10 to the negative 4 coulombs. Okay, here we would have 1800 microcoulombs, and here we would have 2700 microcoulombs. Our total capacitance, we would just add them. So we have a total capacitance of 9 plus 9, 18 microfarads. Therefore, a total charge stored, we would just add up all these charges, or you could think of it as 18 times 3, which I'm just going to write this one in regular coulombs. 18 times 3 is 54, and then we got the zeros. So 5,400 microcoulombs. Okay, cool. Okay, cool. Let's go ahead and try the series one. Okay, so it's the same 3 capacitors, but now they're connected in series. So we got the 3 microfarad connected to the 6 microfarad, connected to the 9. Oh, nope, sorry, they are not the same. I lied. They are a 6 microfarad and a 10 microfarad and a 15 microfarad capacitor connected in series to that 300 volt battery. Okay, now the charge on them we know is all going to be the same, but we don't know that total charge yet. So what we're going to need to do first, the only thing we really can do first, is calculate our total capacitance. Okay, so to calculate our total capacitance, I'm going to do 1 over C total equals 1 over 6 plus 1 over 10 plus 1 over 15. And I can plug that into my calculator. 1 over 6 plus 1 over 10 plus 1 over 15, and 1 divided by that gives us a total capacitance of 3 microfarads. Okay, so from Q equals delta V times C, or C delta V, 3 times 300. Okay, again, I'm going to put this in microcoulombs. Gives us 900 microcoulombs of charge. So it's going to be 900 microcoulombs on each individual capacitor. Okay, and then since we know their capacitance, okay, 6, 10, 15, we can just find that voltage from delta V equals Q over C. Okay, so we got 900 microcoulombs divided by 6 microfarads. So the micro and the micro cancel out. So we got 150 volts for this one, and 90 volts for this one, and 60 volts for that one. And of course, we always want to check that indeed they do add up to that 300 volts. Okay, cool. Okay, cool. Now, last but not least, let's go ahead and solve for the equivalent capacitance of this complex circuit. So in this one, we would first combine these two that are in series, okay? And we would have 1 over C total equals 1 over 6 plus 1 over 3. So that equivalent capacitance is going to be 2 microfarads. So in our circuit, we got that battery and the 4 microfarad one and the combined 2 microfarad one. So the total capacitance is 6 microfarads. Okay. And that's it for capacitance. Okay, cool. Okay, cool.